So hi everybody, I'm Ogden Maric. I'm a senior researcher at Definity. So this is a continuation of the last week's tutorial on verifying canisters using TLA. So basically we didn't quite make it all the way through, and then a few more people asked to see, so we covered kind of the basics of TLA, and a few people asked to see more realistic examples of how you can apply TLA to things like canisters and so on. So that's what we're going to do this time around. So yeah, if you haven't seen the first part, it might be a bit difficult to follow unless you already know a little bit about TLA. Okay, so let me now start sharing my screen. Good. I'll keep an eye on the chat window if you have any questions. Right, so just as a kind of a refresher from what we saw the last time, so we looked at this traffic light model where we use it to illustrate a few basics of TLA, such as that it uses state machine model. We saw some basic TLA formulas. We saw how to use VS Code as an IDE for TLA, and we looked at some TLA analysis tools. Now, we also looked at another example. This is Peterson's mutual exclusion algorithm. So we use this to see how you can model control flow using program counters. And then we saw a little bit more of TLA, so some like operators with arguments, quantifiers, function updates, and so on. And then we also saw, this was already a bit short in time, but we saw some basic properties. So how you can specify invariants that TLA or TLC in particular can check for you, so the analysis tool. And today the agenda is as follows. So we look at the interaction between governance and ledger canisters. So I'll now show this in a bit more detail. So I'll give you kind of one approach how you can model interactions between canisters. And we'll see some examples of some more examples of invariants, so some more complicated invariants. And then after that, we'll look at people parties. So we will look at how we modeled connection establishment. So people parties are sort of a Dapps, so it has a front end and a canister backend. So it's kind of a full-fledged application built on top of the internet computer. And we'll use this as an example of how you can approach modeling front end and canister interactions. Then some of the properties in the people parties model are going to require us going beyond invariance. So I'll use it to give a brief intro to temporal logic as well. And we'll see some tricks how we can model stability properties in particular, which are relevant for this project. And finally, I'll wrap up with some thoughts on coming up with your own specifications and models. So this is one of the questions that popped up. Okay, so let's dive into it. So I'll just give again a brief refresher on how governance and ledger work, and then we'll look at the model. So for our purposes, you can think about ledger just basically keeping the balances of different accounts. And for our purposes, we just distinguish between two types of accounts, so governance accounts and user accounts. So the usual flow of interactions is as follows. So you have some user who in the account C has 10 ICP. Then the user can send these ICP to a governance account, say account B. Then they are transferred there. And then the user can actually issue a claim neuron call to the governance canister. The claim neuron call is then going to, or the governance canister is then, as a consequence of this, going to go to the ledger and query it about the state of the target account, so in this case B, and it's going to go back to or answer to the governance canister and say, well, here the current balance is 10. The governance canister then updates what's called the cache stake. So it says, okay, this is 10, and it actually then locks this stake for a while. During the time that this is locked, the user can use this cache stake to vote on proposals. And after some time, the neuron becomes unlocked again. So this is simplified again. There are things like maturity and rewards and so on, but we're not interested in those right now. But basically, once this locking period elapses, the user can issue this burst neuron call to the governance canister, which then goes to the ledger canister and instructs it to transfer the stake somewhere. So for instance, the user could instruct the canister to transfer the stake here to account D. And then once the ledger completes this transfer, it can it informs the caller, so the governance canister, which then reduces the stake to 0. Okay, so this is how the interaction looks at the high level. Now let's look also a little bit at how we're going to model this using TLA+. So I'll just describe the main ideas at a high level, and then we'll dive into the code. So I'll do less live coding today because the models are getting more complicated and I don't have time to really code everything live. But I'll just go through the main ideas, and these are kind of them at a high level presentation style. So let's look at the claim neuron. So this is kind of pseudocode for the claim neuron call. Let me get the laser pointer. Okay, so the claim neuron, you give it an account identifier as the parameter. And there's also this TID parameter, which I'll describe in a second. So the claim neuron, what it does, it just asks the ledger for the balance of this account ID. It awaits a response, and then once it gets the response, saves it to the balance variable, and it updates the cache stake of this account ID to the balance. Now I'm going to use color to represent information that we will need to store in the state. So cache stake is an example of such information. And I mentioned that I will explain what this TID does. So the idea is that each time you call claim neuron, there can be multiple calls rather to claim neuron, and we want to basically distinguish between them. So to each call, we associate a thread ID. So this is similar to the Peterson algorithm, if you remember from last week. So this is why we add this other parameter, thread ID. So also we use this when we took the ledger canister to distinguish between different methods. So which one is asking for balance? Okay, so like I said, we were going to ask the ledger to something. So we will need some also code, pseudocode for what the ledger does. So we'll have a query method at the ledger end, which is going to await a request, and it's going to receive the thread ID of the requesting governance canister, or the requesting method on the governance canister, and the account ID. And it's going to respond to this request by just returning the balance of the asked account, right? The account that was asked. So here we will also need another piece of state to record the balances. So this is kind of obvious, right? We already had these in the previous slide. Okay, so what's maybe a bit less obvious is that we will also need some additional data to model this in TLA. First, we are going to need things like requests. So basically, when we will need to have a way to communicate between these two. So in reality, this will be done by the internal computer, right? So once your canister issues a request, this will go, the internal computer will basically handle this and dispatch this. But in our model, we need to add, so we need to model this explicitly. So the internal computer actually gives you a guarantee that if one canister issues 2 requests to a target canister, these will be delivered in order. So we will make our requests in the model an order structure, so a list. And there we just record what was asked, right? This is the thread ID, it's asking for this account ID. And similarly, we will need responses, so we'll need to store responses somewhere. So this is going to also go into the state. So this is going to be another piece of state, both requests and responses. And this is where we put responses from the ledger canister, right? So hopefully not too surprising. Now we will need also something more. If you look at this claim neuron, so the flow of information is, or the flow of control, let's say, is going to be, you're going to ask for the balance. This is going to put something in the requests. At that point, other things can happen. Then the ledger will respond at some point, and then eventually you'll pull this response in. So we will need to create several transitions that correspond to this single sort of structured method. And we have already seen how to do this in the Peterson example, Peterson's algorithm example. So we are going to introduce labels here, at least visually, and then we will do something similar in the code. So basically, we'll have one transition from going from each label to the next label. So to record where we are currently, we will also introduce another piece of state, which is going to be the program counter. And we have also seen this in Peterson's algorithm. So we start from the claim start. And there's going to be one transition that's going to move us from claim start to claim wait, and it's going to put something in the request. So it's going to put this request there. Now, we will need another transition that is going to correspond to this part here. And when we do this, we have a bit of a difficulty because here we will need to update a cache stake of this account ID, but we actually don't have this information stored anywhere. And to correct this, we will add another piece of state, which is going to store the arguments of each thread. So when you call something, like we call claim nor, we're going to store the arguments for later use in another variable that we're going to add, so some args variable, just call it like that. And then later we can pick it out from the from our in our second transition, basically, yeah, just picking out which account ID we're dealing with. So, right, in summary, these are kind of all the variables that we are going to need. So we're going to need the cache stake, the balance, these two are the obvious ones, and then the less obvious ones are the program counter, the requests, the responses, and the args. So at this point, I'll just note that there is actually this +cal language, which basically does exactly what I've described now. So it kind of desugars this structured kind of procedure-based structure of programs into several transitions. So you can write code that looks pretty much like what I've written here, and you'll automatically get the corresponding TLA definitions. I didn't now introduce +cal because I don't have time to go into it, but this is something that you might want to consider. We did use it in practice when creating these models. Okay, so much for the high-level picture. Let's now dive into the code. I'll now share my code here. So, okay, all right. So this is the model. Actually, give me 1 second. So what I will try to do is also paste into the chat. I think this is the repository that actually holds all this code. So you'll find this part 1 and part 2. So this is the same repository as the last time. It's just I've reorganized the code a little bit now. So basically, right, you can find everything that you found last time. I'll still code some bits of it live, but only a very small part. So I have this live directory, which I'm going to be using. So like I said, I want to write everything now here live, but I want to explain some or point out some really important details of the model. So the first thing I want to focus on are these definitions here. So what do these do? So it depends on the definition. The first one, for example, we use this definition to set the user balance initially to 2 for all users. Now, okay, why do we do this? So, well, we have to start from certain initial states. Could be 1, it could be more. We could start with a larger number. So we could still say, okay, we set everybody's account to 1,000 ICP, for example. The problem with this is that then you have a huge state space explosion after this, because if you have, let's say, 2 users, the user could transfer 1 ICP to somebody else. So you would get 1 state for that, and maybe they could transfer 2 ICP to somebody else, and so on. So the number of possibilities just explodes. So we have to basically restrict our model to some small number of states, right? And this is what all of these definitions do. And this is kind of the price that we pay for getting automated verification, because TLA is just, we push a button, we write the property, and we don't have to worry about it, which is very nice. But basically, we very soon run into problems with huge state space. So you need to constrain the analysis. And for the purposes of this tutorial, I kind of restricted it, even more than I would in the actual analysis. But it actually doesn't go much more. So even in the actual analysis, we didn't have many more kind of components of the state. So for example, another thing that we limit is the number of neuron accounts. So we're going to look at only the setting where we have 2 neuron accounts, 1 user account. We are also going to look at only 2 claim neuron threads and a single dispersed neuron thread. So meaning that if there are problems that could arise once you have 3 calls to claim neuron, we would not catch them with our analysis, at least not with TLC. So this is something to keep in mind, and you will have to do also for your own models if you're using TLA. And what are the what's the size of the different parameters that your analysis tool can handle? Well, to answer this, you'll need some experimentation, and you'll also need a little bit of experience to kind of get some intuition where the interesting cases could lie. So which parameters do you maybe want to make larger at the expense of some other ones, which might be less interesting? Okay, and then after those constants, we have a bunch of other things. We say, okay, accounts are neuron accounts, union user accounts, so these are sets. We have a bunch of constants for the labels. So these are different labels that we're going to use to structure the control flow. And we are also going to have a bunch of auxiliary operators to help us with things like communication between the canisters. So we want to exchange both queries and transfers, because when you disperse, if you recall, the governance is going to instruct the ledger to actually transfer some money. So these are here for that purpose. And here's our state space. So these are the variables. This is kind of what we described before. So we have balance, cache take, request responses, and so on. Okay, so I'll now point out a few other interesting things that where we might run into some TLA syntax and things like that we haven't seen before. So we'll start with the initial state predicate, and here how it's defined. So first, it requires that the balance has to be equal to this. And what is this? So this is a combination of 2 functions or 2 maps. So I'll maybe use maps. It's probably easier for people who are not so used with to dealing with functions. So you can think about it as a map whose keys are in neuron accounts, and the value for every key is set to 0. And you combine this. So this is an operator. So this add operator is defined in the TLC module. And in the beginning of the file, actually, I can scroll up. So in the very beginning, we have a list of modules that we import. So this is the extends clause in TLC. Right, so we combine this map with this other map of user accounts, where every user account is mapped to the initial user balance. So basically, every user has the initial user balance, and we already have one user according to our definitions, but this is obviously easy to adjust. So what this operator does, it creates a new map where if you look a key up, it's going to first look it up in this map, and if it doesn't find it, it's going to look it up in this one and return whatever it finds, including undefined if the key is not present. Meaning that even if we take this map here and we just say for every account, you map it to the user balance, initial user balance, the result would actually not change, because for every neuron account, you would still look it up in this map, and the only remaining accounts are user accounts, and you would look them up in this map anyways. So the result would be the same. Okay, so that's the balances. For the cache take, we're going to set it to 0 for every neuron account. Requests and responses are going to be empty. The difference is that requests are ordered. If you remember, I was mentioning that the internet computer provides you this guarantee that requests are delivered in order. So this is an empty sequence in TLA, and this is the empty set. So responses are not ordered, so we'll use an unordered collection such as set to basically to store them. Now the arguments are going to be a map from any thread ID, either claim thread ID or disperse thread ID, to the empty set. So we're not storing any arguments in the beginning. And for the program counter, the claim thread IDs are going to start at claim start, and the disperse thread IDs are going to start at disperse start. Okay, so this is not so new, but we can look at what claim neuron looks like. So as I mentioned, we're going to have 2 different transitions that correspond to the claim neuron method. In the first one, we'll require that the current program counter of this thread ID is claim start. And we will then change the state to change the requests. We are going to have the same requests as before, except that we are going to append one element. This is this query from the thread ID for this account ID. And we're going to change the program counter. So now the claim neuron, this claim neuron thread or method is going to move to the next state. So it's going to move to the next label. So this is the function update syntax that you already saw the last time. So this says that the new value of the program counter is the same as the old value, except this argument where it's a claim weight. Okay, and for arguments, we're going to save the arguments. So this is kind of new. We haven't seen this trick before. We're going to update the arguments and say, okay, the local argument of this thread ID is going to be this account ID, such that we can retrieve it later. Now, once this is sent to the requests, what can also then later happen is that the ledger can actually respond to this request. And this is the transition that corresponds to or that models this. So this models this query function that we saw in slides. So to be able to respond to a query, well, first requests have to be non-empty. So this hash here means not equal to. So requests should not be equal to the empty list. The request, we take the first element of the request. So this is a let-in construct. It's like just a local definition, similar to a let-in Rust or OCaml or Haskell or something like that, if you're familiar with that. And then we ask that this first element of the request should be a query, because it could also be a transfer request. What we're going to do is then we're going to add something to the responses. So we're going to say that the new value of responses should be the same as the old one, except that we add another element. So we union it with set with a single element, which is the response to this. And the response is going to contain the balance of this account. And then we're going to kind of dequeue the request from the head. So we're going to remove it, basically, the request that we have already processed, we have just processed. And we're going to change the request to drop the first element. So this is what the tail does. Tail is defined in the sequences module. So this is one of the built-in modules of TLA+. And then we have a claim neuron weight. And this might be also a little bit interesting, because here we have this existential quantifier. So this, remember, this is just a predicate in two states. So this means that if you can find, if there exists some response from the set, such this predicate is satisfied, then this transition can be done. So in particular, this means that if there is some response from this set of responses where this thread is actually waiting for a response, this is a response to a query, so it's not a response to a transfer. It mentions in particular this thread ID. So it's really meant for the current thread. Then what we can do is we can update the cache stake. And here we're going to use this arguments that we stored before, arguments of thread ID, such that we can update the cache stake exactly at this point. We update it to response.value. We also remove the response, similar to the way that we remove the request. And we move the program counter to the end of the claim neuron procedure. Okay. So this is claim neuron. Now, similarly, we have dispersed neuron. So I'm going to skim over this a bit more. But what this does is it first appends the request to transfer something to the ledger. Then there's also another transition on the ledger that's going to allow transfers to happen. And here we're going to just change the balance. So we're going to update two things. Each request has a from and to field, and we're going to basically subtract the amount from the so from balance, or the balance that's actually here identified by request.from, and we're going to add something to the balance of request.to. And finally, we're going to send a response to this, and here's the response. And then this response is going to get picked up by this dispersed neuron weight. So this is a similar pattern that we saw with claim neuron. There exists a response and responses, and there are some checks being done, and then you update the cache stake to set the value of the arguments to 0. So sorry, of the saved arguments. So this is the account ID that this person is operating on. You set it to 0, and you remove this response. Okay, so these are the claim neuron and dispersed neuron methods, and now there's also another transition here, which is the ledger user transfer. And this one basically transfers some money from user account to neuron account. And it picks any amount between 1 and the balance of the user account and updates the balances to subtract the amount from the user account and add it to the neuron account. And then we have our next relation, so our full transition relation. It's basically a big existential quantifier. So say if there exists some value that any of these things is satisfied, then this is a legal transition. So either you claim the neuron, so either of the two phases, either of the two transitions, or disperse the neuron, or create a ledger, transfer something, or do a user transfer. Right. And we also allow explicitly here that we don't do anything such that we don't get warnings about deadlocks, because we know that once we have performed all of our two allowed claim neuron calls in our disperse neuron code, we will actually run into a deadlock. So we kind of expect that. We have also seen that, I think, previously with the traffic light example. Okay, so this is the model. Let's see what we can analyze. So we have specified the model, but we have actually not specified what we expect from it to happen. So here you will see all the definitions here. And if you look at all the properties, if you look at 3A canister and 3B canister, as in the previous attempt, 3A is going to have some flaws and 3B is going to contain the fixed version. So you can look at these offline in more detail, but I'll write out some potential desirable properties. Okay, so I'll write the property here. So here's one potentially useful property, and this would be that the supply doesn't increase, right? We don't want the supply of ICP to increase by doing this, which would just be shuffling ICP left and right. So I'll have a supply stays constant operator. So how is this going to look like? Well, it should be basically, I've already defined this sum f here, so I've done this already for myself. So this says sum the values of the function f on all elements of the set S. So if I say sum the f balances or balance on the set accounts, so this gives me basically the sum of the balance of all accounts. So this should stay constant, and this should be the same as the initial user balance times the number of user accounts, right? And I can have, so there's a cardinality operator that's defined in a finite sets module that I can use for this. So this tells me how many user accounts there are. Okay, and I can now save this and I can run this. So Control-Shift-P, check model with TLC. Okay, sorry, supply is constant. I actually defined it differently in the configuration file. So here's the configuration file. Sorry, here we go. So it says supply is constant. Actually, stay on by supply. I'll write that one in a bit. Sorry about that. Okay, but this is basically what I now instructed TLC to check. So let's now check again. I did not save the other one. Okay, let's try and save that. And let's try to check again. Okay, let's see what happens. Okay, this is taking a little longer because Zoom, but we haven't found a problem. So far, so good. Okay, see that there's a question now, sorry. So the question is, why are the requests modeled as a single list and the responses in a single set rather than having a collection of lists representing message streams between every ordered pair of canister threads? Okay, so the requests are actually, so they are ordered between every pairs of canisters. So they're not necessarily ordered between threads of threads, so different invocations of method calls. So meaning that if you have a claim neuron and a disperse neuron call that both talk to the ledger, it's if you would have separate streams for all of these, then you wouldn't know which one came first if you had one call coming from claim neuron and one call from disperse neuron. For going the other directions, we could have a collection of sets, for examples. That wouldn't really, that wouldn't be a problem. Okay, we have also something in the Q&A section. Let's see. I can open this. Right. So the questions were, sorry, to what extent can you generate TLA from Raspberry Tuckle code currently? We cannot currently. We're actually looking into this. So this is something that we want to do as a project. So we will be working on this in the following few months. And another question was if there was a mathematical proof for the initial user balance. Right. Okay. Why did I use 1? Why did I just not use 3 or something? So it was a little bit of experimentation. I basically wanted to have something that's fast enough for the tutorial, so for this presentation. So I found that 2 works well. Unfortunately, this is what I said. This is like a problem with TLA. You have to come up with these bounds, and they're somewhat arbitrary. So you have to have a little bit of a feeling like, okay, maybe some interesting things will happen if I increase the supply of ICP. So I can't give you, unfortunately, a good rule of what you should do, and it's definitely, there's no proof that this is correct. It's kind of just yeah, you have to go a bit by gut feeling. So the results of this analysis, they have to be qualified. They only hold for certain things. Okay. Right. So we had this invariant, supply is constant. This worked out. So are we now done? Well, maybe let's think about other things that you would like to hold. And here's another example. So maybe we would like to say, well, if the supply is constant, it's bounded by this number, then the cash stake should also probably be, well, it shouldn't be equal to this number. We know that it doesn't have to be equal, but it should not exceed this number, right? So this is what we had. Actually, what did I call it in the config? Doesn't matter. Let's say that we have, we're going to call it cash stake is bounded. And we now want to say, well, we want the cash stake of all the neuron accounts to be smaller or equal than the supply. And this is the supply. So, okay. Let's now go to the configuration file and say, well, I'm going to copy this. So cash stake is bounded. Okay, this is the new name. So I'm going to say, check this invariant 2, please. So can you enter a state where this doesn't hold? So let's see. And the answer should be actually yes. Right. Okay, so we're actually going to find error. So how does error happen? Well, let's look at maybe it's going to give us like a sequence of steps that led us to this error. And we will see the last error here in this sequence. And in this state, we're going to end up with both neuron 1 and neuron 2, so neuron account 1 and neuron account 2, both having a cache stake of 2. So this is pretty suspect, right? Because our supply is actually 2, so we now suddenly have 4 in cache stake. So how did this happen? Well, we can go through the error trace, and here TLC will helpfully tell us like which of the transitions did we take to get to the state. So we see that we started from the initial predicate, then we did the claim neuron. And here we can actually use this args to see what did we call the claim neuron with. So we called it the neuron account 1. Okay, well, at this point, there's actually nothing in this account because this account has 0. Okay, let's see what happens. So now simultaneously, while we put this request in, actually user came in and they simultaneously transferred some money to this account. And there is now suddenly 2 ICP in this account. Okay, so far so good. Then the ledger query happens. So the query that the claim neuron method actually issued to the ledger, it gets processed, and here's a response. So you'll see these M markers here. So these mean that some part of the state was modified, so you can easily find what was changed. So we'll see here that, okay, there's an answer from, so this is the thread ID for claim neuron 1. This is a query, and the value is 2. So yeah, this neuron or this account currently has 2 ICP. Now the claim neuron is going to look at this and going to say, okay, I get the response. I'm going to update the cache stake to 2. Okay, so far so good. Okay, now we start dispersing the neuron. Which neuron do we disperse? Well, here's the arguments of D1. We disperse neuron 1. So this is the one that we just kind of claimed. We transfer now the balance. So this is also all good. Now we transferred from neuron 1 account to neuron 2 account. And then the user simultaneously issues a claim neuron for this method for this second account. And now I can probably see what's going wrong, right? So the balance of this second account is actually 2. So once the ledger queries the account, it's going to say, well, here's our answer. this account currently has 2, right? Cache take or has a balance of 2. And the claim neuron is going to update this to cache take of 2. So now we suddenly end up with 2 neurons with cache take of 2. And this is actually an example of a problem that we really saw in the wild or in our NNS. We fixed it in the meantime. But this is, of course, a slightly simplified example, but this is an example of a problem that could happen. So yeah, I won't go into details of how we fix the problem. You can find this in the in 3B canisters at TLA if you're interested. But yeah, a little bit short in time to discuss that now, fortunately. Okay, so this one is an example of, oh, sorry, I did not mean to stop sharing. This is an example basically of what can go wrong or invariant go wrong. So we saw some slightly more complicated invariants. But now let's look at some more examples of other projects. So we look at how to look at 2 canisters interacting. The question is now, can we look at also at full apps, so which also have a front end? So let's look at the people parties app. So what is this? So this is a project where people try to verify that other users are real humans. So what happens on your phone, you have something like you get a video stream of another user and the location. You're supposed to say, yes, they're in this location or not. And they have like 1 minute to get to actually convince you that they're where they claim to be. And you can click approve or deny. And then the next round starts. There's another user who gets another minute to do the same. And you again click approve or deny. And then you actually take your video and you stream your video, and other users say approve or deny. Okay, and how this is implemented is basically there's a canister that contains some control data, and the users are running some front-end code, which is some JavaScript that's basically created by the canister, and they establish audio and video connections among themselves. Now, the team that was implementing this in the because this is experienced engineers, it is still finding or running into problems with connection stability. And we wanted to use formal methods to eliminate the bugs in this algorithm. Now, we wanted to eliminate bugs in the algorithm. It doesn't mean that the system is correct, because you could still have problems with libraries and so on. But at least the algorithm wants to get right. Okay, so what are some of the properties that we want to have? So some basic invariants were that we don't want more than 1 inbound connection, because you wouldn't know which one to display probably, or the app would get confused. And it would not be clear if you approve or whom are you now approving. And what we also wanted to have is that we don't have simultaneous inbound and outbound connections. Okay, so these are kind of invariants that we saw as before. So I won't go into a lot of detail about these, but I will show you roughly what the model looks like. So I'll describe some main properties of the model. So here you'll find, again, 3 files now this time around. It's going to be, sorry, let me close all these. So I'm going to show for A connections. Very good. Okay. So I'm not going to go into detail about everything here, but I'll just point out some the kind of at a very high level what the model looks like. So we're going to have a list of participants who are participating. They're grouped together, and they are trying to prove to each other they are people. And then we're going to look at our state. This is going to be a little bit interesting. So the state is going to have only 2 components. One is canister, but not just the canister. It's actually going to keep the entire history of the canister. Why are we doing this? So the idea is that if your app is going to issue queries to a canister, you don't know which version. So even though the canister, well, okay, you might not get the latest state of the canister, because queries don't come with such guarantees. Meaning that you can hit a replica that has an arbitrarily old state of the canister. So the approach that we took is basically to keep a list of the history of all states that the canister has gone through. And then the participant just kind of arbitrarily reads from this list of possible states. All right, so I think this is kind of one thing that you could take away if you want to model any kind of Dapp that uses queries. And then we also keep the state of each participant. And we can look quickly at what these states look like. So this is an example. This is an initial state of the participant, of every participant. It has just 2 components. It has a list of video connections, which is going to be an empty map initially. And it has a canister read. So this is kind of the index into this canister history of the last version of the canister that the participant has read. On the other hand, the canister is going to take this initial state. So it's going to take a sequence. Again, this is a history, if you remember. So this is the history of the changes that this has already gone through. So we already start with some history. So it's going to go through an uninitialized state where you don't even know who the participants in a group are. Then you start from the initialized states where you know who the participants are, but you haven't actually started the party. And there's the init active where you actually start with around, in this case, 0. So now there's a particular participant who should be proving, so who should be sending video to the other ones. And then the initial state is quite simple. So for every participant, you map them to this initial participant state. And for the canister history, you just take this init canister. Okay, so this is the initial state. And then let's quickly look at the next predicate. Okay, so the initial state says basically there should exist some P1 and P2. So again, as long as one of these is satisfied, we can take the step. So there are several things that the participant can do. It can refresh the connection. It can finish the party by reading a state from the canister that says the party is finished. It can start negotiating video with somebody else. So if it thinks it's the prover, it will go and start negotiating video. It can establish video, so either as the initiator of the connection or the recipient of the connection. It can reject video. It can lose video. So this can happen basically. This is like spontaneous loss of connection. So this is like models and network problem. It can detect video loss. So if the problem already happened, you can lose the connection just by detecting that the problem already happened. And finally, you can pull the canister. So you can basically read the latest state of the canister or some state of the canister. It might not be the latest one because you can hit an old replica. And finally, there are two actions or two different transitions that change the canister state. So the canister can update the round it's currently executing, and it can finish the entire party. Okay, now for the properties, we'll see there's a bunch of invariants here. So these correspond to the ones that we have already specified. So every participant set, and for every other two participants. So this is a little bit maybe an interesting formulation. This says that if the participant P basically has a connection to P2 and it has not initiated it, so the initiator is set to false, and the state is established, so it's an established connection, and same for P3, so it's an inbound connection, meaning it, so basically the initiator equals false, it's an inbound connection, and it's established. So if you have two such connections to P2 and P3, then P2 and P3 have to be the same remote participant, meaning that you can only have one such connection. And similarly, we have an initiate all or none, but I'm not going to go into details here. Basically, what I'm trying to do, so we have a bunch of invariants, but we've kind of already seen how to specify invariants. So if we can run into a state where these doesn't hold, TLC would complain, and then it would run into, we would see an error trace. Okay, so these invariants or invariants in general are what's known as the safety properties, meaning that they say that your system doesn't do something unsafe. But what they don't actually specify is that your system does anything. So one easy way to have a system that satisfies all safety properties is a system that doesn't do anything because, well, it doesn't do anything, so it can't do anything bad. So the question is, well, how do we verify that our system actually does something useful? So there's a cheap way to do it, and it's actually to use invariants to sort of negate what you want to happen. So here's an example. I'm going to say here I have an invariant that says that for every two participants, either there's no connection, so somehow there's no connection between them. It says either P2 is not in the domain of participant video, or if it's in the domain, so there's some kind of connection, or at least it's not an established connection, right? So this is saying you will never establish a connection. So what I can do now is I can go and ask TLC to check this, and I hope that it's actually going to come up with an error and say, no, this doesn't hold. If this doesn't hold, this means that I'm actually able to get to somewhere useful, right? So this is a good sign. So this is something that I actually want to be violated. But what this doesn't tell me, so this tells me that I can establish a connection, but it doesn't tell me that I will establish a connection, that I have to establish a connection. So the question is now, how could we specify something like that? And I'll show a little bit more on how we can do this. So the question is, what do we actually want? And here's the way to specify what we want. What we want is actually, if you remember, this is what we started with, we were saying that there are problems with connection stability. So what we want is that the prover establishes a stable connection to every verifier in every round, right? So let's say we take round 2. So we have this green bar, meaning that we have stable connections. So we want to have stable connections in round 2 from the prover to everybody. Okay, now once you start thinking about it a little bit harder, you're like, okay, this is maybe too strong, right? We have to qualify the statement. Namely, if the network is unstable, then, well, obviously we cannot have that, right? It's just going to be dropping connections. And actually what we also need to have is we need the network to be fast enough, right? Even if it's stable in the sense it's delivering all the packets, if the latency is like 1 minute, well, you only have 1 minute to do the round, so this doesn't help us. So we have to qualify that this should hold only if the network is stable and fast. Okay, now what you can also immediately think of is that, well, if the prover and the verifier would crash, well, again, tough luck. So we have to qualify this again. And similarly as for the network, they also have to be fast enough. So they have to respond to things quickly enough. And now when you start thinking about responses, you go like, okay, well, actually, there's probably going to be a delay. So we have to somehow account for some kind of a delay right here, because they're not going to be able to establish the connection immediately. So we're going to say after some delay, they're going to establish a connection, right? And then you think about it some more and it gets even more complicated, because you say, okay, well, what if there's a network hiccup here or here? Well, we still probably want to be able to establish some kind of connection for the period where there are no hiccups. So we want to say that if the network is stable for long enough at the right time and so on, and so on. So it gets pretty complicated, right? So actually in this project, we could encode all of this, but then the analysis would get quite complicated. So I'm going to show you one trick that you can use for such stability properties, where we actually move to a different model that's less realistic. So it's a bit of a simplification, but it's actually still useful. And here the idea is that we had this target round where we wanted to look at stability. So for example, round 2. So the idea is that let's see what happens if we freeze the target round. We kind of stretch it to infinity. Okay, and then once we do that, we can try and establish actually stable connections here. And it becomes a bit easier to qualify this statement. So we can say that if the network is forever stable eventually, so meaning there might be a bunch of hiccups, but after some point they stop, okay? And similarly, the provers and verifiers, they stop crashing at some point. Then what we want to have is we want to have an eventually stable connection from the prover forever. So we have something, forever stable connection. Okay, and this is kind of what we'll now try to analyze with TLA. But in order to analyze it, we need to specify this. And invariants are not going to be enough for this. So we need a more expressive language for specifications. And the language that TLA uses is linear temporal logic. So I'll give you a crash course in linear temporal logic. So what do we need to define such things, so to specify such systems? So first we need the notion of a trace. A trace is just a sequence of states that complies with this init next predicates. We've already seen this last time. And then once we have a trace, we can say that the trace satisfies a predicate. Basically, we just look at the first state. We kind of ignore the rest, and we say it satisfies P if PFS1 holds. Okay, so this might look a little odd, but we're ignoring everything else, but it kind of falls into place a bit later. So then we can also say add what's known as a modality. So we can say add a box operator. So this box P, which is read as always P. So we say that the trace satisfies always P if P holds basically in every state. So if you look at this, it just has P everywhere, right? So if you think about invariants, they're actually you can write an invariant using this box. So invariant is always P, right? That means P is an invariant. So we have already seen this, right? It's just a different way to write this. Nothing spectacular so far. But we'll now add something new. So we'll add the eventually, or the diamond operator. So trace satisfies eventually P if the P holds for some state in the trace. Now you can also say that trace satisfies diamond box P. So this is, you can parse this as this way. I'll give you a few seconds to think about it maybe. So like, what would this be? Okay, so the answer is basically, this is eventually always. So it means that there is some point in the trace where P starts holding and then it always holds after that. Okay, and similarly, we'll have something, you can flip it around and have box diamond. So the question is, when does this satisfy, when the trace satisfies box diamond? So again, I give you a few seconds to think about it. Okay, so this is satisfied if P happens infinitely often. So basically, for every J, there's an I greater than J. So okay, this is the formal thing, but basically this means that P should appear, infinitely often in the trace. So there are infinitely many points where P appears. Okay, so armed with this, actually we can almost go back to our people parties model. We need one more thing. So these liveness properties, they require that something happens, like eventually something will happen and so on. But there's sort of a problem, which is not necessarily a problem in reality, it's more a problem with our model. And this is that basically our traces may not be fair. So what does this mean? So here's an example of a simple state machine. You have just one initial state where X is 1, and you have one transition that takes it back to the same state, and you have another transition that goes to a different state. Now, this state machine allows the following trace, where you just stick basically to the first, you just keep looping in the first state. Now imagine that this is basically let's say, a state where transition A, this is the model of a distributed system where transition A means that the first system, so the first node, takes a step, and this transition means that the second node takes a step. So this means that this state machine would allow basically executions where just one node takes steps and the other node never does anything. So this is kind of an artifact of the way that we model things. It's not really a realistic problem. So one thing you can do is that you can introduce a weak fairness constraint on the model that says that if this transition B is forever enabled, then you're not allowed to ignore it forever. Okay, and this is what we're going to need in our model, and it's going to disallow traces like this. So I'm going to quickly jump back to the demo. So this is going to be O4B connections.tla. So this is going to have a bunch of more definitions. I'll just quickly skim over them. So here, remember, first we wanted to stretch our target round, and here the target round is given by P to infinity. And how do we do this? Well, we're going to introduce a constraint. You'll later see in the connections.config, there's a constraint that says that this should, or actually might be ignored in the next predicate, I'm not sure, that says that this has to hold. So you're not allowed, basically, we disallow the system for progressing past the round where P is the prover. Okay, so we stretch this round to infinity. And now we have a bunch of these fairness conditions. So we say that things that can happen, they must eventually happen. We require this. So here are some examples. Basically, if you can update the round, if the canister can update the round and it doesn't update the round beyond the prover, then it is going to do this. So you're not going to get stuck in some round before your target round just because you have other things to do. And similarly, we have fairness constraints in negotiating video, establishing video, detecting video loss, and polling canister. So if you can poll the canister, a participant will eventually poll the canister. You can't just keep postponing this forever. So this is what the fairness conditions say. And now we have the stable video connections property. So here's kind of what we want to have. So we want to have basically the connections from P should be stable. And this is the way that we specify this. So we use this diamond box. So this is this eventually forever. So this means that there's some point after which this is going to hold forever. And what's going to hold is that P is going to have a connection to P2, and the state of this connection is going to be established. And moreover, we want the same in the other direction. So we want P2 to have a connection to P, and this connection should also be established. And because of this eventually forever, we should have, so this should hold eventually forever. So we require, again, remember this is this TLA syntax where this is just a way to write a conjunction. So it means both of these have to hold. So either that, because we have this here, or so either this has to hold, or one of these things have to hold. So these things basically say which are the bad things in which we give up. And the bad things are, well, if the participants start, or they just keep refreshing their connection. So here we have infinitely often, so we have this box diamond. If they infinitely often refresh their connection, well, you can't have stable connection, so we're okay with not having that. And also, if they're infinitely often just lose video, that's also okay. But we don't want the, so this is a little bit technical, but it's basically saying that it's okay for them to lose video infinitely often, but it shouldn't be the case that this is just detecting video loss. So it shouldn't be the case that they have already lost video, but they're just detecting it. And also there's basically, there are similar transitions where a participant will just decide to drop video if it pulls the canister and sees that it should enter the new round. So we're basically saying this means that this is spontaneous video loss. So it says if P spontaneously loses connections infinitely often, then we don't guarantee anything. Okay, so that's basically it for this model. Again, we're not going to actually check this because I'm, again, almost running out of time. But here are the specifications. So you can actually run this. You can find this in the repository. If you run this, you'll find that there is a counterexample. So you'll actually run into a problem trace. Now, this is going to be a little bit interesting because it's going to tell you that it's a loop. So you'll actually find a loop where some things happen infinitely. And you can get out of that loop and you never do the right thing. So basically, you infinitely keep doing the bad thing. And then you can look at 4c.connections.tla. You can try and spot the difference. But basically, this is the fixed version where the property holds. Okay, and maybe just a quick, so that's it, what I want to say basically for people parties. I just wanted to quickly give a couple of thoughts on specifications and models. So ideally, you have a specification. In the ideal scenario, you have bad systems and you have like a very nice boundary between good systems. And you can use this to give your specification. And your system, you know, it has a slightly different boundary, but hopefully it falls into this, right? So this is kind of the ideal scenario, but more often it's actually not easy to specify things so neatly. We have just seen an example of this connection stability. So your specification, you know, it has rougher corners, so you have to kind of make it, it's not so easy to specify. And at some point, the specification can become super complicated where it's like as complicated to specify as the system. And it's hard to reason whether you even think like, you know, you see the specification, it's hard to even say, is this actually, you know, a good description of a good system or is it a bad description of a good system? An example would be something like a self-driving car. Like it's you know, should the car turn left or should the car turn right? Who knows? And here are like a few things to try if you're struggling to come up with a specification. So you don't have to specify every desirable behavior. So your specification doesn't have to be complete. We can try to specify some aspects. So formally specify some clearly desirable behaviors. Start with simple properties. This is also another option. So this is a way to find like a subset of things that you can specify. Try invariants. So these can be very useful and they can be easy to find. You can collect obviously bad states and behaviors and see whether you can generalize from there basically to get invariants. And then if that fails, some other things to try are basically to change the game, like what we did with the people parties example. And one last thing is actually just look at a bunch of examples. Like I tried to give you a few. If you look at the TLA repository, they have a bunch of examples of algorithms, so you can see how to specify things, how to model things. And you know, you basically get good at it with practice. That's it. Okay, bang on time. So this is the last slide. I see there are a few questions now, but I don't know how we proceed with them. We can have time to answer. Yeah, questions are how to ensure that the source code of an app maps to the bounds and that's guarantees of the TLA model. You don't. So it's just basically you bound TLA model and you know that it's not going to be exactly the same, but you hope that you chose the bounds well enough that it doesn't matter. Okay, yeah. Yeah, I think that's it. Then we can wrap up. Okay. No, we don't need another session. Thanks, Anna. Okay, I think then that's it for today.
Yogi.
Well, thank you everyone for listening. I hope that was useful.
Thank you very much, Ogi, and thank you for attending. Goodbye.